We're going to study higher order differential equations now. Everything we've studied so far has been first order differential equations, meaning these are differential equations involving an independent variable, let's say x, a dependent variable y, and the derivative y prime of x. So now we're going to consider situations where we need to have y double prime, the second derivative of y, or even the third derivative or fourth derivative. Now, strictly speaking, it wouldn't be true to say that we haven't considered any of these yet. The falling satellite problem, the falling rope problem, any problem that used f equals ma was a second order differential equation, but we didn't really treat them as such. We just kind of made a substitution. V equals dy dt, and then turned it into a first order differential equation and solved it as such. So this is the first time that we're really going to look at how to solve second and higher order differential equations in their own right without transforming them into first order ones. Right, so we have equations that look like this. That's what we've studied so far, where we have some kind of equation involving x's, y's, and y primes. And these are first order equations. So this is the sort of abstract notation for a first order differential equation. Any first order differential equation can be written in this form. For example, a separable equation, if you wrote it as y prime minus f of x g of y, it would equal 0. It would look like this. And then we had first order linear equations. That was the other type of equation that we learned how to do. That was applied to rocket launch with air resistance and mixing problems. So now we're going to consider equations involving higher derivatives of y. So if the equation involves y prime, y double prime up to the nth derivative of y, then it's called an nth order ordinary differential equation. So here's a physical example leading to our first higher order differential equation. We're going to have a mass attached to a spring, where the spring has a certain spring constant that says basically how hard the spring is to compress. And we're also going to suppose that the object experiences resistance to motion proportional to its velocity with this proportionality constant beta. We're going to write a differential equation, and then we're going to solve the problem. So we have a mass, it's on a spring, and we're just going to assume that it's experiencing two forces, the force of the spring and the force of resistance. We're even ignoring gravity right now. So let v equal x prime, that's the definition of velocity usually, and acceleration is x double prime. We know that force equals mass times acceleration, and we know that there are two forces acting on our object. The spring force, this is always the spring force by the way, is minus kx. This is called Hooke's law, as mentioned here, and this force is the force of resistance, which we're assuming is proportional to velocity. So we have these two forces, and so F equals ma turns into this equation. If you move these things over to the left-hand side, you have this pretty simple looking equation, just constant times the second derivative plus constant times the first derivative plus constant times the function itself equals 0. Notice, by the way, that x depends on time. We are interested in how this object moves. So suppose we were to pull it down and then release it, we could expect the spring to cause the object to oscillate up and down. So this is the differential equation we have once we plug in our mass, resistance, and spring constant, m, beta, and k respectively. So this is a second order differential equation because it involves the second derivative of our unknown function x of t. So there's a lot of words that we use to describe this equation. First of all, it's second order, as I just mentioned. It's homogeneous. That's just a word that we use to say that that the right-hand side is 0. And soon enough we'll consider inhomogeneous equations as well, where we have some function of t on the right-hand side. Ordinary differential equation, well, we know what that means. It's a differential equation where there's one independent variable, which is time in this case, and constant coefficients. The coefficients of our unknown function and its derivatives are numbers rather than functions of time. And, well, here are the explanations. So, I mean it when I say straightforward. Solving equations like this, it's always done the same way. Always just guess that your solution is going to have the form e to the rt. Turns out this always works. So you just kind of remember that, and if you do, then observe that if you want this to be a solution, you need to be able to plug it into the differential equation and get 0 equals 0. That's what we mean by a solution, as always. So notice that the first derivative by the chain rule is r e to the rt, and the second derivative is r squared e to the rt. And so when we plug this in for x prime, this in for x double prime, and this in for x, the equation, our differential equation, becomes this. Give you a moment to take that in. And if we divide both sides by e to the rt, then we obtain this equation. Now, interestingly, this is not a differential equation at all. It's an algebraic equation in R. It's a quadratic equation in R, to be precise. So, to recap, so far we started with this differential equation. We guessed that the solution would have this form. When we plugged that solution into the differential equation, we found that it would work provided this was true. And if you don't understand how we got here, I do recommend you carefully go through the previous slide. You definitely want to understand how we got this equation, this algebraic equation. We apply the quadratic formula, or just tell Mathematica to n-solve this equation, and you get these two solutions, or roots, as they're called. So our guess works provided that we take r to be one of these two numbers that satisfies this equation. So we have two different solutions to our differential equation, e to the negative 0.23t and e to the negative 0.87t. They're both solutions, so I encourage you to check that if you plug either one of these solutions into this here equation, you get 0 equals 0. And not only that, but any linear combination of these two solutions is also a solution. What do I mean by that? I mean that we call this solution x1 and we call this solution x2. Then I encourage you to check that if you take any constant multiple of x1, like say 3, so 3e to the minus 0.23t, and then take any constant multiple of this solution of x2, and you add these two things together. That's called a linear combination, in case you haven't taken linear algebra before. Any linear combination of these two solutions is also a solution. So this is our general solution to the original given differential equation. The general solution is any linear combination of these two guys. For example, suppose we stretch the spring by 1 unit, 1 meter, I guess, and we start the object at rest. Then we'd say that x of 0 is 1 and x prime of 0 is 0. And we could use these two initial conditions to find C1 and C2 using this code. Let x of t be C1 e to the, just let x be exactly what we wrote here, and then solve these two equations for the constants C1 and C2. And you find, so that's two equations and two unknowns, C1 and C2. And it is happy to tell us the answer is this. So C1 is 1.475, C2 is negative 0.475. And so this is our particular solution. It's the solution to this initial value problem with these two initial values. So that's an interesting and important point, is that when we have a second order differential equation, we can deal with two initial values rather than one. And you might recall from the first homework, when you were doing the steel beam problem, it was a fourth order differential equation, and there ended up being 4 arbitrary constants, and so we were able to deal with four initial conditions. So you got a system of 4 equations and we're able to solve for the 4 constants. Here we have a second order differential equation, so there are 2 constants, and therefore 2 initial conditions can be satisfied. Here's a plot of our solution, and just as it's supposed to do, it starts off with 0 derivative, and it starts off at a value 1. And it does something not terribly surprising. The spring wants to bring the object back to equilibrium. Now, perhaps you were expecting, however, for the object to sort of oscillate back and forth over the equilibrium position, because that's kind of what you expect an object on a spring to do. However, there was a resistance of a certain amount, and it turns out that resistance was so much that it slowed the object down so fast it didn't even pass equilibrium. So it's interesting to see this solution, that the object does not oscillate back and forth. However, if we lower the resistance, as we do in the next problem, you will get that oscillating behavior. So let's suppose we have an object, I believe it's the same mass and spring constant. Maybe I changed them, I can't remember. But let's suppose that the resistance is brought way down to 0.05 kilograms per second. Then we're going to write the differential equation for the path of the mass and solve it again, just like before. So once again, we velocity is x prime, acceleration is x double prime. You can generally skip all this stuff and just go straight to here. I mean, everyone just memorizes this, which I'm fine with. You don't have to go through the F equals ma stuff. Mass, resistance, and spring constant. This is a popular problem. Comes up in every differential equations course, really. So the mass is 2 now, the resistance is 0.05, spring constant is 0.4. And as before, as I told you to do, we will simply guess that the solution will have the form e to the rt for some number r. So we plug it into the differential equation, and we get this, divide by e to the rt, and you get this. I believe I failed to mention this equation in R is called the characteristic equation of the differential equation. So just to be clear, you start with a differential equation. It was 2x prime prime plus 0.05 x prime plus 0.4x equals 0, and we transform it into an algebraic equation in terms of this number r. So if you do the quadratic formula on this, you don't find any real numbers r such that this is true. You find that they are imaginary roots or complex roots. They have imaginary parts. Here's what they are. I just found them numerically. And they could also be found with the quadratic formula. And so now we want to say that our solution is e to the r1t, and our other solution is going to be e to the r2t. But what does it mean to take e to a complex number power? Well, there actually is a formula for that. So first of all, let's plug in r1 to get our first solution. And how do we deal with this I? Let me show you. First thing we do is we take the real part and move it aside. So we have this. This is a real valued thing. But then we have e to the 0.447 ti. And it turns out you can rewrite this term as cosine of thing plus I sine of thing. And that's Euler's identity, that e to the I times a thing is cosine thing plus I sine thing, where the thing in this case is 0.447t. So let theta equal 0.447t in Euler's identity, and you get all this. So again, we started here. We split the exponent apart into this real part and this imaginary part. The real part we left alone, and for the imaginary part we applied Euler's identity, which is this. Now this is still kind of troubling because we have an I in our answer, and we don't like having I in our answer because, well, it's not clear what it means to for our mass to be at an imaginary position. So right now this is not a physically meaningful solution. But if we just continue anyway, dealing with the second root the same way, we take the real part and deal with the imaginary part using Euler's identity. The only thing that changes is now we have minus 0.447 instead of positive 0.447. So we have this, and now something wonderful happens. It turns out that the real part of this solution is a solution to the differential equation. And the imaginary part, if you get rid of the I, also so happens to be a solution to the original differential equation. So I'll let you take that in for a second. We found a complex valued solution to the differential equation, and then it turned out that if we just took the real part, called it x1, and we just took the imaginary part and called it x2, then those are solutions to the differential equation. I'm not going to prove that, I don't think, but it is true. And then, as before, any linear combination of these two solutions is again a solution to this differential equation. So in general, we have the general solution. I factored out the e to the minus 0.0125t, and we're left with c1 cosine 0.447t plus c2 sine 0.447t. This is our general solution. And as before, we have two constants, c1 and c2. for example, if our object starts at position 1 with velocity 0, same exact problem, or same exact initial values as in the previous problem, then I guess I didn't write the Mathematica code, but you would do precisely the same thing. You would define x of t to be this expression with c1 and c2, and then you do that same n-solve thing that I did on the previous problem. So you end up getting these two values for c1 and c2, and so this becomes your solution to this initial value problem. So this is our solution. I thought I'd graph it for you. And as promised, we have that oscillating behavior. Why is the amplitude decreasing? Well, I can explain it, first of all, based on our solution. The amplitude is decreasing exponentially because of this term out here. As the oscillating behavior, of course, is coming from the sine and cosine. So this solution tells us how fast the amplitude is decaying, as well as what the period is, so tau over 0.447, if you need to know. What else to say about this solution? Yes, well, why physically is it decaying? Well, it's because of the resistance. The beta, the resistance to motion, is causing our object to slow down. And so as it slows down, it sways a smaller and smaller amount. It oscillates with an ever-decreasing amplitude. And this might lead you to conjecture that if we had no resistance, beta were 0, then you'd have a perfect sine or cosine curve without any decay in the amplitude. And that's actually the case, as I think we'll see soon enough. I just wanted to, even though I'm not making this course about complex analysis, I did want to state the things from complex analysis that we are using. First of all, I assumed Euler's identity. So I assumed that we can take e to a complex power. I assumed that it makes sense to say that the derivative of e to a complex power is e to that same power. In other words, that the rules of differentiation hold even for when we allow complex numbers, and that the chain rule also holds for complex numbers, which it does. And then we also assumed that this is just a restatement of Euler's identity, and that all the usual rules of exponentiation hold true even when doing complex exponentiation. And finally, we made this weird assumption that if we have a complex valued solution to a differential equation, then the individual components, f of t and g of t, are also solutions to the differential equation. I mean, this fact is what allowed us to make any use of any of this stuff. If this weren't true, then using complex numbers would be completely useless. It's this fact that once we find a complex solution, we can look at the real components, and they are solutions as well. That's what makes all of this stuff useful in finding solutions. So the last two problems looked like this. And for both of them, we just guessed that the solution would have the form e to the rt, and then we solved the characteristic equation by the quadratic formula. And if we got real roots, then there was no problem. And if we got complex roots, we just used Euler's identity to deal with that situation. It turns out you can do this for any order equation, not just second order equations. So I state that as a theorem here. If you have an equation, any nth order homogeneous ordinary differential equation with constant coefficients, where the constant coefficients have been labeled A0, A1, A2, up to AN, then you can always guess that your solution is going to have the form e to the RT, and then you just have to figure out what R is by solving the associated characteristic equation. This is just a restatement of what we already did, except instead of it being second order, it's nth order, if that's clear. And you'll always find n roots. Not necessarily distinct roots, but you'll always find n roots. That's a consequence of what's called the fundamental theorem of algebra, which they're supposed to teach you in high school, but they usually don't do a very good job of it. So let me remind you, the fundamental theorem of algebra says that if you have a polynomial equation, polynomial equals 0, where the polynomial goes up to nth degree, then you have n solutions, or if you're allowing for complex valued solutions, and if you count repeated solutions with their repetitions. If you have these roots R1 through Rn, then your general solution is always just going to be the arbitrary linear combinations of those n solutions e to the RT. So this is the general solution. Only there's an asterisk here, and the asterisk is that you have to do something a little bit different if you have repeated roots. We haven't looked at that yet. And the other thing is that you have to interpret complex roots with Euler's identity. But besides these two little hiccups, this is how you solve such equations. So here's an example of a fourth order differential equation. Don't read into it too much. It definitely doesn't apply to any physical situation that I'm aware of, but let's solve it. First we look at the characteristic equation to figure out what R has to be. And R, well, Mathematica is happy to factor it for us. And this is an interesting topic, abstract algebra, where you can learn about how Mathematica is able to factor things like this. Uses pretty advanced mathematics to figure this stuff out. But anyway, we're happy to use this without understanding how it works for now. So this is the factorization, and that leads us to, we have 4 roots as promised. 2 of them are complex, coming from this irreducible quadratic term, and then 2 more of the roots are real, coming from these linear factors. And so when we have complex roots, we interpret it using Euler's identity to give us this part of the solution. And then for the real roots, we just put them up here as 1/2 and -1. And so this is what a solution looks like when you have these roots for the characteristic equation. And finally, I need to tell you how we deal with repeated roots. So here's an example of a differential equation that has the repeated root issue. Here's how we deal with it. As usual, we want to solve the characteristic equation. Here it is, but it has a repeated root of -2 and -2. That's what I mean by a repeated root, in case you forgot what that is. -2 is repeated, and so you might be tempted to say, well, shouldn't our solution just be C1 e to the -2t plus C2 e to the -2t? But you quickly see that that's nonsensical, because if you made this your general solution, then you could just combine these constants together into one constant. So you've really only found one solution. You haven't really found 2 different solutions, and we really want 2 different solutions because we ought to be able to deal with 2 initial values. So you should not be content with this solution. We need more. We're greedy. We need two independent solutions. The way you do it, first of all, you have your regular C1 e to the minus 2t, just as before. Then your second solution is tc2 e to the minus 2t. So what you do is you multiply your second solution by t. That's the trick. In general, here's the rule. The repeated root exception, as promised. If you have a root, r, and it repeats q times, in this case it repeated twice, but if it repeats q times in the characteristic equation, then you replace the corresponding part of the general solution. Instead of c e to the rt, you replace c with a polynomial of order q e to the rt. So, one final monster of a differential equation to sum it all up all at once. Here's a seventh order differential equation, and we solve the characteristic equation. So that's it. And we factor, and we get this. So now we have, alright, so these are our factors. Here they are. The factors, the roots are 2, then -1 repeats twice, and plus or minus I repeats twice. The repeated root rule, along with Euler's identity, gives us the following. So the 2, nothing happens there. You just get c1 e to the 2t, nothing special. Because we have -1 appearing twice, we have c2 plus c3t e to the -1t. And then because I, since plus or minus I repeats twice, you use a polynomial coefficient of cosine t and a polynomial coefficient of sine t. Right, so we're pretty much just going to do second order equations, unless I find some wonderful application of higher order equations. I'm sure the applications are out there, I just haven't been made aware of them yet. So if anyone finds anyone in my class finds a third or higher order differential equation, besides the steel beam problem, that was one example, I am definitely interested to hear about it.